All right. Good afternoon, everyone, and good evening to whoever is listening from Europe. My name is Giulio Carducci, and I am a computer engineer from Turin. I've been a research fellow in the Department of Philosophy in the University of Turin, together with my colleague Marco, which is also here today. The goal of our project was to study and analyze a corpus of metadata about PhD thesis using data science, natural language processing, and information extraction techniques in order to derive meaningful information from this corpus. And today we are going to talk about one of the achievements we obtained during this period. The title of this work is Semantically Aware Text Categorization for Metadata Annotation, and it is focused on the bibliographical categorization of records when very little information is available. More precisely, this is the research goal. So given an arbitrary set of unlabeled documents, is it possible to identify all documents that belong to a specific class? And in our particular context, the class we are going to consider is the philosophical class. This is a brief description of the data set we had available. So it contains nearly 500,000 records of metadata about PhD thesis, English PhD thesis, collected by the British Library. It contains a list of informational data, but the most informative ones are the title, abstract, and subject, which is a synthetic description of the area of study. This work is motivated by the need of the philosophers from the University of Turin to know which of these documents among the nearly 500,000 ones were philosophical, because documents belong to all areas of study. We had the subject field, but it is a free text field which is not standardized, and it could not be employed for such a process because there was not a rule that guided it. Also, the manual inspection of documents was not feasible given their number. So we chose to employ a binary classifier, which given a record can tell us whether it is philosophical or not. I've said that the documents of the abstract, but only nearly 40% of them had this information available. And we can see a distribution of data, and we can see that the documents with abstract tend to be more recent and distributed in a smaller time span. However, the abstract information accounted for nearly 95% of the total word count, so making the dataset really unbalanced and biased towards the records with abstract. For this reason, we chose not to employ this information for our work, and we relied only on the title, which was available for all the documents. However, in order to build a classifier, we need to gather a sufficient number of training samples from which the classifier can understand the structure of a philosophical document and then extend this knowledge to previously unseen documents and to classify documents that are not labeled. We did not have a label for the documents in the dataset, so we applied a simple heuristic by extracting all the records that contained the substring philosophy in the subject field. This is, of course, an approach that is prone to error, but it's still a good starting point for our research. This resulted in a total of nearly 3,500 documents, from which we asked the domain experts, so the philosophers from the university, to annotate 500 of them in order to be 100% sure that those documents were philosophical. And then we extracted a number of negative documents 10 times bigger than the positive ones, because the classifier needs to be able to distinguish between philosophical documents and not philosophical documents during training. So at the end of this process, we had a training set composed of 3,300 documents, both positive and negative, and a test set composed of 1,000 documents, 500 of them philosophical and 500 of them not philosophical. So the goal is to train the classifier on the training set and then test its performance on the test set to assess its overall performance. The classifier we chose to employ is random forest, which builds a number of decision trees that analyze the feature of our documents and output a label, which is 0 for non-philosophical documents and 1 for philosophical documents. We chose this model because it can handle a large number of features pretty well, and also it provides a measure of their importance. Thus making the model partially interpretable, which is really important because we are able to tell when, for example, a classifier, when, for example, a record is classified as philosophical, we are able to tell why the model has made this decision, which is a very important aspect in machine learning and data science. However, we cannot feed raw textual data to the classifier because we first need to convert it in a way that the model can understand, so into numbers. We chose to transform data using the TF-IDF transformation, which is beyond the scope of this meeting, so I will not go deep into this, but just consider that for a toy example like this one, consider a corpus composed of 3 total documents. Then we have then each document is mapped to a vector, which is simply a list of numbers that is as long as the total number of unique words that appear in the corpus. Then the integer measures are converted into a floating number, which idea is words that are more informative and more discriminative for the documents tend to have a higher score. So, for example, the word "I" and the word "and" appear very often in the corpus and have a very low score, while words that are more discriminative and more rare tend to have higher scores. So after this process, we transform each record in our training set and feed it to the classifier together with its label. So the classifier can learn to distinguish between philosophical and not philosophical documents. After the process is completed, we can do the same with the test set and compare the labels predicted by the classifiers to the actual labels of the documents. And by doing the comparison between those values, we can we can have a measure of the performance of the model. However, before introducing the experimental result, I will let my colleague Marco talk about the second classification step that is aimed at improving the overall performance of the whole system. Thank you.
So my name is Marco Leontino, and I'm currently a researcher at the computer science department of the University of Turin. And I will introduce to you the semantic model that we developed that consists of different information extraction tasks that are based on the BabelNet knowledge base. BabelNet is a knowledge base that has been generated, automatically generated from the free encyclopedia Wikipedia and the lexical resource WordNet. WordNet represents the meaning of different words using sets of synonyms that are called synset. In particular, we analyze the titles and the abstracts of the thesis that we had obtained from the ethos service, And we define an algorithm made of 3 different steps to collect lexicosyntactic pattern. And the first step is the named entity recognition that has been developed using the Stanford Core NLP libraries. And in particular, we recognize the persons cited in the titles and abstract. The second step is the multi-word expressions extraction that uses different part-of-speech patterns. In particular, we consider the nouns followed by nouns to recognize, for example, sequences such as belief revision or quantum theory. And also we consider the pattern adjective followed by noun to recognize, for example, analytic philosophy. And we also consider the pattern noun followed by preposition followed by noun to recognize, for example, philosophy of mind. Now, from the previously described steps, we have a set of candidates that we have to filter in order to remove the meaningless ones. And to do this, we define the third step, that is the BabelNet search. And we select only the candidates that we can that we could find in BabelNet. In this way, if a candidate is not found in BabelNet, probably it has no senses associated to it, and so we can conclude that it is meaningless. Moreover, we also, sorry, Giulio, could you, thanks. Moreover, we also define a technique to recognize terms related to the philosophical domain. And in particular, we considered only the candidates that were in some way related to the concepts philosophy and philosopher, considering in particular the semantic relations is a and occupation. To recognize people whose occupation is philosopher and to recognize particular types of philosophies. So please, thanks. So in this way, we obtain an array of selected candidates that we call the philo-entities array. And the decision rule to decide if a thesis is philosophical or not is really simple, because if this array, this list is empty, we conclude that the thesis is non-philosophical. Otherwise, we conclude that it is related to the philosophical domain. It is also important to observe that this set of philo-entities could provide an explanation about the content of the particular thesis, because if we consider the example in which the title is dialectic in the philosophy of Ernst Bloch, our algorithm could recognize 2 different concepts that are philosophy and dialectic, related, mapped to their particular Babel-Sinset ID, and also the named entity Ernst Bloch. So this is an example of thesis that is recognized by the decision rule as philosophical. And the particular entities and concepts could be used to compute similarities between different theses related to a particular domain. Okay. Talking about evaluation, the system was evaluated on the dataset that was previously described by my colleague, and all modules in this case consider only the title information, because this was the only interesting information that was available for all our records. And we considered 3 different scenarios. In the first one, we considered only the random forest module and analyzed its results. In the second case, we considered the semantic module and we analyzed its result. And in the last scenario, we defined an hybrid system executing the semantic module only if a record is predicted to be non-philosophical by the random forest approach, trying to improve the the recall of the random forest model. And we can see the results in this table. And we can see that the random forest model has a good precision value, but a poor recall, while the semantic model did not decrease too much the precision values, because it is similar to the one of the random forest, but it improves the recall. So we have a lower number of false positives. And considering the hybrid approach, we can say that it is generally better because it has a lower precision, but a better recall of about 22%, that is about 22% better, comparing it to the one of the random forest model. And so the accuracy is generally better for the hybrid approach. Okay. Talking about explanations, considering the 1,000 records of which the test set is made, the 496 explanations were generated, and they were correctly made for philosophical record in about the 79% of the cases. And it is also important to observe that when both of the modules, random forest and semantic model, agree on recognizing a record as a philosophical one, the phyloentities array contains an average of 1.78 elements, while this value was lower for the cases in which the random forest model predicts the non-philosophical label and the semantic model correctly overrides this prediction. And so this could be an evidence of the fact that probably these cases are in effect more difficult to predict as philosophical. Okay, so we have described a system for categorizing bibliographic records and to automatically characterize the metadata, and our approach is interesting because it tries to integrate domain-specific knowledge acquired by a machine learning approach described by Giulio with general knowledge that is embodied in a particular semantic network. And the system integrating both modules works generally better than the individual software modules. As future work, we could think to improve the explanation techniques and also to explore additional semantic relations, maybe considering different knowledge bases that are less noisy than BubbleNet, such as, for example, Wikidata, that has been annotated by human experts. And thanks for your attention, and if you have questions, please ask. Thanks to everybody.